So in order to do logic with sets, we will introduce something which will take value true and false, but it will itself have some variables, parameters, and depending on the values of those parameters, which will be numbers, peoples, and so on, it will have potentially different values. We will call those things, those propositions with a variable, a predicates. So P of x is a predicate which may be true or may be false depending on what x is. And x is a placeholder, is a variable name that stands for some value from a set which we will call a domain or the universe of P. So just a convention that we usually use lowercase symbols like x, y, z, or words for the names of variables. And usually we'll use P, Q, and generally capitalized words to mean predicates. For sets, I think here I've been writing the whole word capitalized. For predicates, I'm just capitalizing the first letter. So for example, if we are writing x, that probably stands for some element of some set. And if we are writing P of x, P probably stands for the name of a predicate. For example, P of y, or P of name, or even of x. And by the way, the names really are just names. They don't matter. If you take P of x and change it to P of y, well, you just change the name. Well, unless that x was used somewhere else to mean something, and you want to make sure you're using the same name because you want to refer to it elsewhere. So by itself, P of x is not true and it's not false because we don't know what x is. But when x in P of x is replaced with a specific thing, specific object, specific element of its domain, what we call instantiation, make an instance of a predicate, then it becomes something that either true or false. For example, if we have even of x, it may be true, may be false, depending on what x is. But we know that even of 3 has a very specific value. Well, 3 is not even. Feminist Susan has a specific value. Probably Susan is a feminist. And the predicate may be true for some values of x in the domain and false for others. For example, even of x is true for even integers, false for odd integers. Even of 4 is true, even of 5 is false, and so on. Feminist of, let's say, y, to use another variable, is true for some people and false for others. By the way, here it really shows that when you're defining a predicate, it really only makes sense for its own domain, because you can't really talk about even person or a feminist number. Is Stu a feminist? That's kind of strange. Is Susan even? Well, that also is kind of weird. So here you could see that when you're talking about a predicate, there is usually an underlying domain, and a lot of time things will change depending on what its domain is. So here you may say, wait a moment, we just talked about set as groups of objects, and now you're talking about predicates. Are they the same? Are they different? They seem to be talking about similar things. How do they relate to each other? Well, a set is a collection of objects. So a set by itself is not true and false. It's just a bunch of stuff. It's a group of people. It's a group of numbers. It's a bunch of stuff. The predicate, on the other hand, is something that may be true or it may be false. So predicate is something with a truth value. But they're very closely related by the following formulas. You could always, for a given set, define a predicate which is true exactly on elements in the set and false everywhere else. Similarly, you could define a set containing all the values of X from the domain on which some given predicate is true. So for that, you will use the set builder notation. So for the set, you could say set S for the predicate P is all such elements X for which P of X is true. And given the set S, you could define a predicate which is true exactly when X is in S for a given X. Why do we do this translation? Well, because we want to do logic. And in logic, we talk about things that are true and false. So when we do logic, it's much more convenient for us to talk about predicates. So far we talked about sets where there is a whole bunch of elements in no particular order, and the only thing you care about is whether an element is in a set or not in a set. And also we talked about predicates which only take one variable as an input. But a lot of time we want to talk about multiple things at the same time. So a pair of elements, which we will write in round brackets, very different from curly brackets we used before, is just two elements, one from the first set and another one from the second set. S1 and S2 may or may not be the same, but in any case, the order here matters. The pair 1, 2 is not the same as a pair 2, 1, even though the set 1, 2 and the set 2, 1 are quite different. And it doesn't stop at number 2, so we could have pairs, but we could also have triples. And in general, we could talk about tuples of a whole bunch of elements written out in order, which may or may not come from the same set. Let's say just in general, they don't. If you have such a list of n elements, we will call it an n tuple. For example, triple is a 3 tuple. It's a list of 3 elements in some order. Okay, so why do we need to talk about such elements? Well, that's because sets of those things, of pairs, of triples, and so on, come up probably even more often than sets of just elements. So here are some examples. So first of all, we often call a set of tuples of elements, especially a set of pairs of elements, a relation. Because the reason we are making those sets is we look at those pairs, particular pairs, as some kind of relation between the first element and the second element. For example, we could define a relation less than, which is a set of all pairs of real numbers, such that the first number is smaller than the second number. So here again, we use the set builder notation to build a set less than, and every element of that set is a pair, 2 numbers in order. Of course, you say, well, why would you bother to write less than when we have x less than y? Well, here we are doing something different. Here we want to have the whole set, the list of all the possible pairs. So here are some other examples. You could talk about pairs of people x and y such that x likes y. By the way, that doesn't mean that y also likes x. Liking may go only one way. Parent relation definitely only goes one way. If x is a parent of y, y cannot possibly be the parent of x. And here is another example which is closer to computer science. Likes and parents, well, they also come up a lot, but they have less of computer science flavor as this one. Let's define a relation registrations which has triples of things. The first thing would be a name, second would be the name of a course, and the third one would be the name of the semester. And let's have in registrations all such triples such that the first element is the name of a student who takes the course, name the same element, the second element, in the semester, which is the third element. For example, if Wei Li takes COMP1002 in fall 2020, then we will have a triple Wei Li for the name, COMP1002 for the course, and fall 2020 for semester, and this will be an element of the relation of the set registrations. And this is why when you hear people talking about databases, you often hear them call the relational databases. This is exactly this kind of relations. So here is a more database example. For example, you have a database that contains list of all faculty members in our department with a column for their last name, a column for their first name, and a column for their office number. So in this case, you get the relation, which is a set of triples, where the first element is the first name of some faculty member, second is the last name, and the third one is their office. Or you may have a different relation in your database, the one that lists courses, and for every course it lists which days the course is offered, at what time, in which room, and who is teaching it. That's another relation, now with 5 variables in it, so it's 5 tuples. And it will represent all the courses, for example, offered at a given time. So now, again, we need logic. We need logic to query such databases. And for that, we will need to extend our notion of predicates a little bit to allow us to have predicates with several variables, not just one. Because you may want a predicate for that prof data, which wants to take 3 variables, one for first name, one for last name, and one for office. Or we may want a predicate for course data, which takes in 5 things. So in general, a predicate is, again, a proposition with variables, where it can have multiple variables. That said, every predicate is defined on a certain number of variables, and you cannot really call it one time with 2 variables, one time with 3. For example, if you're talking about predicate corresponding to the relation parent, you will always be talking about 2 people. Is X a parent of Y? And for any specific tuple of elements, for any specific instantiation of those variables, a predicate will be either true or false. And just like relations can be binary, to mean that they define on pairs, the sets of pairs of things, a predicate may be binary or ternary, meaning it defined on triples, or in general, n-ary predicate. So we call the number of variables a predicate takes its arity. So here are some examples. So we could write a predicate less than, which is true on numbers x and y. Again, x and y are just placeholders, if and only if x is less than y. Which means if I take the predicate less than and I replace x with a 1 and y with 2, that will be true. And if I write less than with x being 2 and y being 1, that would be false. Often for predicates that take 2 elements, the binary predicates, especially such common ones as less than, we just write them the way you used to write them, like x less than y. But we still think about it as a predicate. X less than y can be true or it can be false. Similarly, a predicate parent is true for x for the situation when X is a parent of Y. For example, King George is a parent of Queen Elizabeth. That's true according to Wikipedia. And if we define predicate corresponding to that registration relation, remember, for every set we can define the corresponding predicate, and for every predicate we can define the corresponding set. That will be true if a person with a name substituted for variable name takes the course substituting for the second variable in the semester substituted for the third variable. So the first two predicates here are binary because they take pairs of things, X and Y, and the last one is not binary, it takes 3. So let's look again at the relationship between predicates and relation, because it may be confusing. They're almost talking about the same thing. Again, a relation is not something that's true or false. It's just a bunch of stuff. And in this more general case, the stuff can be pairs of things, can be triples of things. It could be individual things too, in which case we talk about unary relation. But in any case, it's a bunch of things. Whereas a predicate is something that takes value true or false depending on what you give it. So for a set, you don't really write a set or a relation R of something. For the predicate, that's how you write it. So for example, the less than relation is a set of pairs of real numbers xy such that x is less than y. Whereas the predicate less than, which we could also write the way you normally write it, is equivalent to the formula, which, surprise, surprise, is the same formula that you use to define the property that pairs x and y need to satisfy when you define the less than relation. So the less than relation is defined to be all the pairs xy for which less than of xy predicate is true. And similarly, less than of xy predicate is equivalent to pair xy belongs to less than relation. So to be in something is also a predicate. Is it in? Yes, no, true, false. So we write, for example, the pair 3, 5 belongs to the relation less than. That means that the predicate less than of x substituted with 3 and y substituted with 5 is true. If instead of 3 and 5 you put in 3 and 2, it won't be in the relation and the predicate will be false.